Okay, good afternoon, everyone. Hope you all managed to join, and thank you all for being flexible and joining today online. I think that was a better decision than kind of risking potentially spreading COVID amongst us. And you can use this same Zoom if you would like to attend office hours after the lecture. Okay, so let's get started. If there are no other questions about homeworks or projects or any of the logistics of the course. All right, seems like not. So let's move forward then. If you have any questions, please feel free to interrupt me anytime. All right, so today we are going to continue with our dimensionality reduction techniques, and we are going to focus on some specific cases. So we are going to talk about multidimensional scaling, linear discriminant analysis, and a little bit about distance metric learning. I will give a setup for it, but I will give the whole algorithm next time. Okay, so let's look into these special cases. With multidimensional scaling, the special case we are focusing on is a situation where we have access to information about distance in between our points or any other measurements, but we have no access to the actual points. And this might be a little bit strange to you for sure. So let me give you a few examples of when do we have information about distances, but not about the actual points. So for example, in evolutionary biology, researchers use genetic data to construct phylogenetic trees, which show the relationships between different species or populations. And the genetic distance between species or populations is often used as a measure of their evolutionary distance. However, researchers do not necessarily have the access to the actual genetic sequences of all species or populations, although they manage to estimate the genetic distances between species or populations. And using those distances between species or populations, they can then derive these phylogenetic trees. Then another example is in wireless sensor network nodes. So in computer networks, routers use routing protocols to determine the optimal path for packets to travel from one network node to another one. And these protocols use a variety of distances, such as distance metrics, such as, I don't know, hop count or bandwidth or delay or whatnot, to calculate the best path. And these routers do not necessarily have direct access to the network topology or the locations of the other routers. So we can get the information about distances between the nodes, but we don't know the locations of the nodes, and we can derive that using algorithm we will introduce today. So there are applications of this algorithm in a node localization or node topology. And then also in molecular biology, you might want to know the 3D model of a protein, but you don't have that information, and you can derive that information from some kind of, again, distances. And these distances are distances between some special atoms in the protein model. And using those distances between those special atoms, you can derive what is the actual structure of a protein. And this is called protein folding. So yeah, there are many examples where we have distances, but we don't actually have the information of what are the actual data points and how to represent them. And we would like to know that.
Excuse me.
Yeah, go ahead.
So can we gain the accurate or real points, or they are only a probability and an estimation?
They're not probability in a true sense of probability, but there are, of course, estimates. You are going to find some representation of that node or protein or whatever the genetic sequence that it should kind of be a good representation of that actual node genetic sequence or protein folding that can then enable you to do something with that, representation of that object, be it clustering or I don't know, whatever else you would like to know.
Thank you.
With locations, it's a slightly maybe more specific, I would say, because let's say, actually I have some, let me see whether I have it on the next slide. Just a moment. Yeah, I have it here. So here we have some kind of distance metrics. We have 5 by 5 metrics. So that means we originally have 5 points. And this matrix here gives us the distance between each pair of points. And if you run this algorithm that we are going to go over today, this multidimensional scaling algorithm, and you want to get a 2-dimensional representation of those original points, you would get something that looks like this. So let's for a moment pretend these are 5 nodes in our network, and this distance matrix is the measure of the distances between the 2 nodes in the network, calculated in some way, be it with the bandwidth or hops or whatnot. Then here, these points would actually tell you this is where that node is placed. And that would be like a 2D representation of the placement. But more realistically, that's probably not going to be the exact location of something, I don't know where, what are the units we use for those locations of nodes. It will probably be just a representation of that you can then do something with.
Thank you.
Yeah. All right, let me just check whether I said everything I wanted to say here. Yes, I did. So yeah, I kind of briefly now mentioned the algorithm, which is multidimensional scaling. So the goal of multidimensional scaling, or we are going to refer to it shorter as MDS, is to, given some distant matrix D of endpoints, produce a typically low-dimensional Euclidean coordinates to these points, such that the resulting points have similar spatial relations to those that are described in the distance matrix. So from a distance metric, we get some representation of each one of these points, here 5 red points, and how they are placed in this low-dimensional space over here resembles what we have in the actual distance metrics. Okay, so let's now go into how to get an algorithm like that. All right, so the first step we have is that we are given our distance metric. So we have D, and just a small digression, I will write the steps of this algorithm, and then you will have this, everything what I write down here will be written down nicely, such that you can have it in an easily readable form later on. All right, so we have our distance matrix D. So this is a distance matrix. And from this distance matrix, we are going to compute something which is slight variation of it. I'm going to denote it as D, and then in superscript as D2. And that's basically a matrix where at each position, we use the same element we had in our distance matrix, but we are going to square it. So it's basically every element in D, every distance is just going to be squared. Okay, so that's our matrix D2. I'm not writing D to the power of 2 because that's D times D, and that's different from what is here where we have each one of these squared. So that's why I'm not writing it like that. And then what we are going to do is called double centering of this matrix D2. So I'll write it down, double centering. And, we had already mentioned centering when we were talking about PCA. So let's go over again what the centering means when we do it once. And we are going to then mathify that a little bit, just because it's going to make our derivations of the algorithm easier. So centering once, if you remember, means that we take the mean of each column of the data matrix. So for every column J, we are going to calculate a mean of this column, J, and we are going to denote the mean as D bar J. So that's going to be 1 over n, because we have n element in our matrix, because matrix D is of the size n times n, and n is the number of points. All right, we are calculating the mean of the column J. So that's going to be a sum of 1 to n, where we take every element in D2. So Dij squared. So this is the mean of the jth column. And then from every point in that column of the matrix that we are centering, which is D2, we are going to subtract the mean of the corresponding column. So we are going to then calculate Dij square, Dij tilde, and I will keep writing this 2 here to be Dij2, which is basically Dij square minus Dj bar. So from every element in our matrix, we are subtracting the mean of the corresponding column. And that means we have centered the matrix D2. So this thing here means that we centered once D2. And if you remember when we were talking about this in the context of PCA, this meant that basically if we had points somewhere in our 2D space that we mentioned, then the coordinate system would be shifted such that the origin is at the center of our data, because now our data has the mean of 0. All right, so this thing here, centering, I will write here once. This thing can be written in a more mathy way. So I will write this as mathify. The same thing. So we are going to introduce a vector. It's going to be vector of all ones. So imagine that this is very bold. That's how we would write it in LaTeX. Then we will have a vector of all ones, and it's going to be n-dimensional. So when we make the outer product of that vector with itself, which means that we take that vector and multiply it by itself transpose, we are going to get a matrix of all ones of size n times n. And then from here, we are going to define a new matrix. This is called centering matrix, which is identity matrix. So identity is, remember, a diagonal matrix with all ones on the diagonal. And we are going to subtract 1 over n of 1, this vector of ones, times itself transpose, which is this matrix of all ones. And this is called centering matrix. So we can use the centering matrix to basically do the same thing that is described here using just a single equation, and that's going to look like m tilde equals to Cn matrix multiplication with D2. So this part here, this is exactly what is described over here. And to make it just a little bit more consistent, I will actually call this Mij tilde without 2. So here we produce the matrix M tilde or tilde M, and each element of that matrix is exactly this thing here, which is obtained in the same value can be obtained by this matrix multiplication of the centering matrix and the matrix we are trying to center, which is D2. Okay, so this is something we know. Is
Hello,
there
Prof. Yeah. In the centering matrix equation, what is that? It is natural log or what is it? ln?
there is no lns here, so I don't know what exactly are you referring to.
In the centering matrix equation, what is the first one in which it is
this one.
Yeah.
So this is our identity matrix of size n. Yeah, so maybe in equals to 1 and then all zeros. Yeah. Yeah, that's in here. And now I can see how you can confuse it for ln as well. Okay, now this was all about centering once. So now we need to center one more time, and that's going to be obtained by having another matrix multiplication. So we are going to define M hat as Cn times D2 times, and then again, Cn from the right. So this is double centering. Double centering. Okay, and this is going to be important for our kind of intuition of why this algorithm MDS is giving us what we want. So from our distance matrix getting us points in this that represent the original data points, such that the distances in this low dimensional space are preserved. So this is going to be important for the derivation, and I will show you in the a slide why exactly we need this double centering. Okay, now from this we are done with double centering. So we had double centered. Now we are just going to do another thing we need for our math, and that's divide this matrix we have just obtained, M hat, with -1/2. So we are going to define our M like that. And this is again just serves for the math and for nothing else. And now from this matrix, we are going to compute the eigen decomposition. Remember, eigen decomposition gives us eigenvalues and eigenvectors, where eigenvectors represent the most important direction in that data. Now data which is represented with them. And then we are going to return BK, which is going to be a product of VK times LK 1 or 2. You might be confused what are VK and LK. These are just the first, so from, let me write it here, from V, we are going to, VK is going to be the first K columns of V. And from L, we are going to take first K eigenvalues. And as always, our K is a hyperparameter. So we are saying what kind of dimension we want these points to be represented in. And usually because MDS is used in applications where we want visualization, K is chosen to be very low, such as 2 or 3, something we can actually visualize. So what you get in the end is N times K matrix. So N stands for the number of points, K is the dimension of the points, so every row in the matrix BK represent the original point. Okay, so this now might be, I suppose, very unclear. Why would we do an algorithm in this exact way? And so what we are going to do now is go over why this works. Why choosing M like this and then computing its eigendecomposition is a good idea. Any questions so far?
Professor, so the points are actually not in lower dimensional space, right? We are bringing the points to a lower dimensional space. How do you ensure there is like no loss of information or data?
That there is no loss information. That's a good question. I mean, for me, it's kind of the way that we are going to now see how this is derived. And then when you take it from that whole derivation of the algorithm will make sense. So yeah, it's kind of like trusting the mathematical framework, I guess. And we are going to go over the actual kind of connection to, motivation for doing this matrix M and then the composition.
Thanks.
Okay, so let's maybe go over that so things might be a little bit clearer. This is just everything repeated. I will actually discard this point because it's not correct. Okay. All right. So yeah, this is everything we have written down before, just nicely in a more algorithmic way. And there is nothing new here. Maybe we can just quickly go over it. We have our distance matrix N times N. We are going to construct D2. And here now I didn't put the brackets, which is a little bit annoying. So I'm going to add them. And we are going to construct our centering matrix. Then from centering matrix, we are going to do double centering of our distance squared matrix. And we are going to compute the eigendecomposition of that matrix, take the first K columns of the matrix with eigenvectors, and take the first K, not singular, but eigenvalues that we have in our matrix L. And from there, we are going to get the low dimensional representation for each one of our points, starting from just the distance matrix. And of course, then because this is one of these very standard algorithms, this is going to be available in scikit-learn. Okay, so let's now talk a little bit more about why this procedure to get from distance matrix representation, low dimensional representation of each one of these points. So, all right, let's imagine we have A. This is going to be our data. So N times the matrix. Imagine this is the original data. So I will write it down. This is original data. So data that we have then found the low dimensional representation of with BK. And imagine we have a similarity matrix S defined with values Sij, where each one of these Sij is defined by the dot product between the rows AI and AJ. So remember, our data matrix is n times d. So each row is a d-dimensional vector representing one data point. And imagine we have defined similarity matrix by taking a scalar product between each one of the rows, so between 2 points. Then, because we have defined the similarity as the dot product, another way of writing S is to take A times A transpose, because basically when we do matrix multiplication, we are multiplying the row with the column. So if we take A times A times A transpose, at every position, we are going to get exactly the scalar product. All right, so this holds if we defined S as a through the scalar product. Okay, so now remember that when we were talking about PCA, we had said for PCA, once we center the data, we are going to take the data times data transpose, this outer product, and we are going to apply the eigendecomposition onto that matrix to get the directions that have the most variations in the data. So if we have defined similarity matrix as A times A transpose, then from PCA, we know that the best embedding of A comes from top k eigenvectors of S. So the best embedding of A comes from top k eigenvectors of S. And then later we have also seen that this is actually the same as top k right singular vectors of A. So here there is nothing new. This is just reiterating what we have done before with PCA and with truncated SVD. It's just that we have now defined the similarity matrix to be A times A transpose. So nothing new here, but I do want to stop and just see whether this is clear so far. All right, I'll take the lack of comments as things being clear. So, all right, let's see how now this brings us to this algorithm. How, knowing that the best embedding of A comes from top k eigenvectors of the similarity matrix is related to the distances, because we do know that distances are in a way related to similarities. So the distance between D, I, J, so the distance between points AI and AJ can be written as a norm between the vectors AI minus AJ squared. And we never use, I think, this equation, but you can write this norm differently like this as AI squared plus AI J squared minus 2 times scalar product between AI and AJ. So this just holds. This is true for the norm. So we can rearrange this a little bit, and then we can say that the scalar product Sij is our similarity, which is a scalar product between AI and AJ, equals to 1/2 of norm of AI square plus AI J norm square minus, and now this here will be minus distance of AIJ square. So I just rearrange this equation here by placing the scalar product on one side, putting the distance on the other side, and dividing by -1/2. All right, so we have that so far. Now, bear with me for a second. We are going to show that there is, when we assume this double centering, we are going to see that this similarity can be connected to the distances. So for a moment, we are going to set AI, not AI, but the first point to be 0 vector. And we can assume this because if we are working with distances, then you can basically shift your points as much as you want, but shift every point by the same amount, and the distances will be the same. So shifting of points doesn't affect distances. So you can shift your points such that the first point becomes origin. That's totally valid thing to assume to do. All right, if your first point is 0 vector, then if you look at the distance of all other points to that first point, d k1 squared, then we know, excuse me, here we have square, then we know from here how much that's going to be. We know that it's going to be equal to the norm of this k point square. Then our second point is origin, and the norm of 0 vector is going to be 0. So we have 0 here. And we know that the scalar product between any point and 0 is going to also be 0. So we have -2 times 0. So what remains here is that the distance between point and the origin is going to be the same as the norm of this point. Okay, so now from here, I will use another column. So here, where are we? Here, each one of these can be written down in terms of these distances. So because they are equal, the norm of every point is equal to a distance to this first point, which is 0. So this is same as di1 squared, and this is same as dj1 squared. So our similarity Sij can be written down. Sij, which is the scalar product between AI and Aj, can be written down in terms of distances. So 1/2. Now we have here di1 square plus dj1 square minus dij squared. All right, and now this is where the double centering comes into play. And I will not go into these derivations because I will use the whole lecture just to go through that. This is all available in the M4D book. And I will invite you to read that carefully. So if we have this double centering, the way we have done it there, and you can look at the derivation in the book, then these terms here, dji square and excuse me, this is, no, this is right. So I underlined the wrong thing. These two terms here, di1 and dj1 are going to be equal to 0. So these two terms here are going to disappear. If you are doing double centering. So what will remain is that your scalar product, if those terms have died, then AI dot product with AJ is going to be equal to -1/2 dij squared. Okay, so now we know that our similarities and our distance similarity matrix and our distance matrix are having this connection if we are double centering. And we also know that if we are doing eigen decomposition of our similarity matrix, we are going to get the best embedding of our original points. And this is why we can, if we are producing, if we produce a matrix M by doubly centering the distance matrix and dividing it exactly by -1/2, see over here, we can, through eigen decomposition, get the best embedding of our original data. Okay, now lots has been said here, so let's stop and see whether we need to go into details of anything further. I will also write this down more cleanly while you are thinking about. Okay. Okay, can I get at least verbal confirmation and then everything seems to be clear here?
Yeah, everything seems clear.
Okay, great. Thank you. Okay, so that's it about why this classical MDS works. Really try to check out this double centering in M4D. It's kind of like just tedious math that's not necessary for us to spend so much time on during the lecture, but everything is clear by just reading those derivations that are given out there. So double centering is really crucial for this whole technique to actually work. One thing I didn't emphasize is that this is just a classical multidimensional scaling algorithm. So just like with k-means, for example, this is multidimensional scaling is actually a set of different algorithms. And the one we have introduced is the classical one, the most standard one, but there are different versions. So just know that you might find different versions of multidimensional scaling, and that shouldn't surprise you because that's more like a set of algorithms rather than just one of them, like a framework. Same with k-means and sketching and other ones we have seen before. Okay, now I want to move to the second type of algorithm that kind of is dealing with different kinds of problems. So now we are going to learn about linear discriminant analysis, and this has nothing to do with the multidimensional scaling. It is motivated for completely separate problem. And I mean, I said something very strong here. It has nothing to do with it. I mean, it has something to do with it. We are still looking for low dimensional representation of the data. It's still under the same theme, and there might be connections that are not obvious to me. So I just want to emphasize that LDA is not an algorithm which gets the distance matrix and try to find the low dimensional representation of the original data. So in that sense, it's different from multidimensional scaling. It is known also as, for shorter, as LDA, but you should be careful to not replace it with something which is called latent Dirichlet allocation, which is used for topic modeling. So these are two different algorithms. Latent Dirichlet allocation is something that is, could be also taught in a data mining class. Why not? We will not talk about it. So just don't, think that these two things are the same, although they are usually abbreviated the same as LDA. Okay, so now let's go actually into the motivation for linear discriminant analysis. Basically, LDA wants to do exact same thing as PCA. It wants to find the component axes that maximize the variance of our data, but we are also additionally interested in the axes that maximize the separation between multiple classes. So here, this data is not really unsupervised because you have information in which classes each data point already belongs to. And this, especially with more traditional machine learning methods, might have helped you to kind of map your data to a more low-dimensional representation where you enforce the separation of the data in the training data that you have available to be able to better learn your supervised machine learning algorithms. These days, I haven't seen people using LDA that much to kind of reduce their high dimensional points to lower dimensional and then apply supervised machine learning setup, at least in the research and at least in NLP research with deep learning. But it is one of these very prominent techniques, so we will go over it, although I'm not 100% sure what is the utility of LDA for supervised machine learning approaches, which also stems from the fact that I work in research on cutting edge models that are all deep learning driven, and then we don't really care about efficiency. For us, the performance is the best thing we can achieve, even though we might have brute force the whole thing, unless you are really in a space where you are working on more efficient or green AI. So the fact that I don't know where exactly LDA would be super beneficial also comes from the fact that I don't work in an industry setup where people really care about using smaller models that can give them fast inferences and be super accurate, which is very different from academia, where we work on open-ended problems that don't have high accuracy yet. Okay, so just to recap, with LDA, we are doing basically what we wanted to do with PCA, where we are finding where our data has, what are the directions where our data has lots of variance, but we are also interested to separate instances that are coming from different classes. Okay, so for that, to go into how the algorithm works, I will use a little illustration over here. We are going to try to maximize and minimize something. And the first thing we are going to try to minimize is that there is not much variation for instances that are in the same class. And we want to kind of separate the instances that are in different classes as much as possible. And to achieve these things, we are going to work with means of these data sets, for the subsets of the data corresponding to each class. So here we are going to have mean mu2. So this is the mean of all the instances that belong to class S2. So mu2, I will write it more generally, mu I is equal to 1 over cardinality of Si. So Si is the set of instances in the data that will belong to ith class. We are going to sum all such instances that belong to Si. Okay, so we are going to have 3 of them here. This one, let's say, is here, mu1. And we are going to also have mu3. I will keep the color consistent, not super important, but makes things nicer to look at. All right, so mu3. All right. So I said we want to minimize the variation inside each one of these blobs. And to do that, we are going to define a scatter matrix within class scatter matrix. So we want, if you look at each one of these distances here, excuse me, it's a little bit hard to illustrate. So here, the distance of this point to the mean, distance to this point to the mean, this point to the mean, this point to the mean. So each one of them to the mean, taking those vectors and outer product of those vectors with themselves, we want to try to make that as little as possible. So each one of these vectors, this is going to make things weird. Let me use another color here. This little vector here, that if this is x, then this is x minus mu2. So each one of these little black vectors is that point subtracted from the mean of that set. All right, so we are going to define here matrix sigma w for within one of these subsets corresponding to a certain class. And so we are going to go over each one of these blobs. We are going to have C of them. Here we have 3. And for each one of them, we are going to look at its points. So X element Si. And then we are going to compute these little vectors, these little black vectors here, which are X minus mu I, where mu is the mean of that blob, times itself. So we are making the outer product and measuring basically the variance within that subset of the data. And we want to make this, we want to minimize variance here. So minimize variance within the class. But we don't want only to do that. We also care about maximizing the variance across these different blobs. So if we find the mean of the entire data mu, so mu is 1 over cardinality of X, where X is original data, all of it, then we want to maximize excuse me, I kind of started to ramble. So we have the mu, which is the mean of our entire data. And then we want to look at the distance of each one of the means of the smaller blobs. So from here to here, from here to, couldn't do that. Okay, here, and from here to here. So we have these 3 distances, and we want to maximize those. We want to separate these blobs as much as possible. So we can do that by defining another matrix, another scatter matrix, and this is going to be in between class scatter matrix. So sigma B, where B stands for in between. We are going to again sum over each one of these subsets of the data. We have C of them for C classes. And then we are going to do again outer product between mu I minus mu. So we are looking at the distance between each of the class means to the mean of the entirety of the data. and making the outer product, because outer products gives us the variance, right? And we are going to also weigh that by the number of instances we have in the subsets of the data corresponding to one class. If your subset of data has lots of instances, it's going to get more weight over here. You want to you are going to emphasize that this distance is larger for that class. So this thing we want to maximize, because we want to maximize variance between classes. Okay, so our goal now is to find directions in our entire data such that the within variance, such that the variance within each one of these classes is small, and such that the variance between classes is large. And we are going to again use the eigenvectors, eigenvalues to find important directions, but we are also going to find those vectors that gives us these properties. So basically, what we are going to do is stuff we have already described. We are going to get the mean of each one of these subsets of the data corresponding to certain classes. And then we are going to compute the within and in between class variances. And I said something. I said, now we want to find the directions in the original data that are going to represent that data as PCA, but that they are also going to minimize the variance within class and maximize the variance across the classes. And it turns out if you define a matrix by taking the inverse of the within class scatter matrix multiplied by the in-between class scatter matrix and compute eigenvectors and eigenvalues of such matrix, then those eigenvectors will give you exactly those directions that do this minimization and maximization I was talking about. And then once you have those eigenvectors, we know what to do with them. We take k of them and we multiply our matrix by it, and then we get a representation of our matrix that lives in n times k space and has all these properties that we wanted to induce. And then again, this is one of these prototypically important standard algorithms, so it is available in scikit-learn. Okay, questions about this whole procedure? You're so quiet today. Usually I have more questions.
Okay, so about the classes, is that like related to like or like clustering algorithms, or would you like to just add clustering algorithms so that you have like labels that have like say clusters and then you know like what are the classes that you want to like try to preserve?
Sorry, Jordan, I didn't really hear you. Can you talk a little bit more loudly if possible?
Okay. So I was just like curious, like how would we, I guess, basically get the classes? Is that already like given, or would we like try to do like a clustering algorithm?
Yeah, so you are assuming these classes are given to you, and yeah, this is typically, so typically you're working now with the labeled data, which is quite different from what we had seen so far. And the idea is that, okay, you want to do some kind of classification, and by doing this projection onto low dimensional space while preserving the distance between classes, you might be able to use your supervised machine learning algorithm better. I doubt that you will ever use LDA as your classification technique without any additional step such as using supervised machine learning algorithms. So you can imagine, for example, using SVM, support vector machines, and instead of working with the original very high dimensional data, you project it with LDA first, and then you apply SVM to the data that's projected by LDA. And the idea is that you should be better, more efficient, and you shouldn't lose much information because you preserve this separation of the data that existed. Now, I have linked in the website this very interesting comment, not a comment, I linked the blog where a nice comment appears, and let me try to find it and read it out loud. Where is it? Okay. I'm lost in the website. Okay, here it is. So here, I recommend reading this whole blog post where you can see how this works on a concrete data set and so on. So might be useful to just go over this in any case. But then they say here, let me try to find it. Okay. All right, so one thing you might kind of conclude is that, okay, this is basically PCA that gives me separation of classes preserved. So if I really want to just, my whole goal of dimensionality reduction is to be able to do my supervised machine learning better, then this should be the better approach compared to PCA. And here it's written that although that might sound intuitive, actually it has been shown that after using PCA for some image recognition task, you can get better lower dimensional representation compared to PCA if the number of samples per class is relatively slow. And so, although it's intuitive that LDA always works better than PCA, it seems like this is dependent on the number of examples you have in each class. And they also say it is also not uncommon to use both LDA and PCA in combination. For example, PCA for dimensionality reduction followed by LDA to additionally separate classes. So that's something to have in mind, but yeah, you get the label data, just to answer your question super shortly. And your goal is typically to do classification. Does this answer your question, Jordan?
Yeah.
Okay, great. Right, any other questions about LDA? All right, so then we are going to move to distance metric learning, which we can also abbreviate with DML, although I don't think it's as common of the abbreviation as it is for, with multidimensional scaling, we had MDS and then LDA. These are super standard abbreviations. And today, I will not derive the entire algorithm. I thought we will run out of time, but since there were not many questions, actually, I could have probably talked more about it. So in the next just 2 slides, I will tell what the goal is with distance metric learning, and then we are going to introduce the actual algorithm next time. We will need a lot of additional notation and math to actually set the algorithm in place. So there will be a little bit of build up with defining a bunch of things and then using those things in the algorithm later on. Okay, so now with multidimensional scaling, we had a problem where we had information about distances, but we do not have information about the points itself, and we wanted to learn the representation, low dimensional representation of the original data. Then with LDA, we had a problem where we wanted to induce in our representations, low dimensional representations of the data, this separation of classes, and we had label data. Now this setup for distance metric learning is different. And here we have this constant thing we are mentioning where features are all numerical. And so far, we always assume they are all given in the same unit. Remember, for example, with SVD, we talked more about this. I gave you some examples, such as you have every data point is a weather station, and you are collecting some kind of weather measurements. And all of these measurements, let's say they are in Celsius, are going to be exactly in the same units across data points. And that was important. But what if you have a situation where your features are numerical, but they are not given in the same unit? So you could have stuff like age, income, height, weight, and so on. These are all things that you can actually quantify numerically, but they all come in different units, right? So one thing that is standard, but very finicky and very brittle, is to use some kind of normalization approaches, such that you scale each one of these things in the same range. So you use some kind of scaling to say, okay, ages are going to be all in range of 0 to 1. Income will also be in the range of 0 to 1, height as well, weight as well. So you kind of artificially set them all to same ranges, and it might seem like they're in the same unit. But this can be very finicky. For example, if you had outliers, if you had one person in your data set which had very widely different age than everyone else, now everything will be going to, all the other ages are going to be squashed in the same, around the same value, kind of artificially, because there was one outlier. So outliers can make a mess out of normalization. You can also do silly things such as, you can set columns in your data that have all the same values, and that doesn't really give you much information if the feature is the same across all the different data points. And then when you do something like this, it's going to make a mess as well. Or we have seen the case where we have data that's dependent, that can be predicted from other features. So we had multicollinearity that also can affect things. So basically, normalization approaches are standard and very frequent, but they are actually can lead to a lot of problems. So instead, what you could do is this approach called distance metric learning, where your goal is to learn Mahalanobis distance, which we had defined like this. You take your difference between your 2 points, 2 d-dimensional points, you multiply it with some d times d metrics, and again, you get multiply that with the difference between your 2 points. And then we will want our metric to be positive definite. That means it will have all those nice properties, such as having d real positive, that is non-negative, positive singular, not singular eigenvalues and stuff like that. Basically, M is going to be have nice properties. All right, so if we learn this M is going to be basically a better way to scale different dimensions in your data, such that you get better scales between them. So it's not like you are going to impose that, oh, if age and income should be in this relationship. Rather, you're going to learn that from the data. And I said here learn, but let's make this a little bit more formal. So given our data, given x in of size n times d, as always, and points of the dimensions, what we are going to optimize for is to find m star that, now bear with me, we are again going to have max min approach. We are going to maximize, find m that maximizes the minimal difference between xi and xj that are far away points. If they are far away points, we want to maximize the minimal difference. I know that max min is always a little bit tricky to map mentally, so let's think about this in a more concrete example. All right, maybe this will be okay. So we know that this point and this point are far away. We also know that this point and this point are far away, and so on. So we can define a set F, which is a subset of our original data. So these are, this just says pairs of original data. So these are going to be far points. And on the other hand, these fellows here, this one and this one, well, they are going to be close each other, right? So we can also define a set C of pairs that are close. Now let's go back to this thing. We can collect all the distances between far points. So this is one distance between far points. This is also distance between far points. This one as well, and this one as well. So we have 4 of them. And we are going to check which one of them is the smallest. Now, this is, as always, I make examples where all the distances are the same, but let's say that this one here is minimal. And we want to find m such that this minimal distance between far points is as large as possible. So we are separating far points as far as possible. But that's not the only thing we care. We're not just trying to, push points far away from each other. We also want to keep those that are close to each other. So we also want to find m, not only that minimizes that maximizes minimal distance between the far points, we also want it to be such that the distance between close points is small, or smaller than some threshold value. So all pairs that are in the set of close points should have their distance smaller than a given threshold. And let's call this threshold kappa. Okay, so that's our goal. Our goal is to find matrix M over here, such that when we define Mahalanobis distance with that matrix M, we get maximal minimal distance between far points. So we are maximizing the distance between far points, and we are also keeping the distance between close points together. And next time we are going to work out how to learn such matrix M from the data. Okay, so I'm leaving you a little bit, it's a cliffhanger, but we are going to see how things work next time. Any questions about this that are not like, but how exactly? All right, seems like not. Okay, then I will stop here because I need to introduce a bunch of new math symbols here, and that's not going to be enough in the following 9 minutes. So we are going to finish now, and then I will stay here for the office hours. If there is no one, then I will also leave earlier. All right, so if you are staying for the office hours, please stay on the same Zoom.
Thank you.
Thank you.
Hi, may I have a question?
Yeah, of course.
Because the concept of eigenvectors and eigenvalues are repeating again, I would like to say I had a hard time learning them, and I didn't found any useful example for that. So if you could share some for me.
Totally. Sorry, guys, let me just try to kill the live stream because usually I kill it by killing the Zoom, but now I can't do that because we need to stay on it. So